Hello, my name is Bradley Hsu, and this is my project, a novel form of TensorFlow object detection to aid the blind in street crossings. So, in the current world, street crossings pose an enormous threat to those who can't see, and the current method the blind use to cross streets are very dangerous because they either have to detect the street through the use of senses, such as feeling the curb or listening for sound cues, or through getting a seeing eye dog, which is both expensive and difficult to maintain. So, I decided to create a technological solution that mimics a seeing eye dog in its ability by leveraging CNN models and transfer learning mechanisms that can help detect traffic light signals. So the hypothesis is that the convolutional neural network model, after transfer learning, will be able to detect signals of traffic lights. So I used Motorola E7 phone, Surface Pro laptop. I tested in Homedale and Red Bank, and I also ran the program on Keras and Android Studio. So the traffic lights, the assumptions are the traffic lights are not being obstructed, and they're all visible by phone. So to start the procedure, I have to first do the model survey, which is basically just surveying all the different types of CNN models to choose a candidate that can be able to be used. And I selected the MobileNet SSD and YOLO 3 model. Then I did an evaluation of both models by running the MobileNet SSD in local street crossings and testing the YOLO model against a large traffic dataset, LISA. Then I performed transfer learning, which is basically just freezing some of the layers and retraining some of the other ones to perform a different task. So I had to re-implement the YOLO 3 model using Keras through transfer learning. Then I had to re-implement the MobileNet SSD as well. And then, and then I created a new model which leveraged that was built on top of the YOLO V3, which leveraged the YOLO 3's original ability to create bounding boxes, but I added more layers for signal detection. So the first step was do a model survey. So I created a model survey of all the different models, and this is the first model, the YOLO 3. And the YOLO 3, one of its main capabilities is this ability to detect at 3 different grid levels and it's able to enhance small objects in the distance. So if you have traffic lights, which are very small in a big camera frame, they can be picked up by YOLO 3 model. And also, it's able to upsample and replicate a lot of the features needed for the dimensions. So that's also very important. And the output of the YOLO 3 was objectness score, which is basically the object name, the multiple class scores, which are the probabilities, and a bounding box around the object. So that's the location. And the SSD MobileNet does very much the same thing, except it's able to adjust the bounding boxes in real time. So it can be used on a phone, and also it can be ported to a phone because it is compatible with Android Studio, and that allows it to be converted to a TensorFlow Lite format and ported to Android devices. Next step, evaluate the models. So to evaluate the SSD model, I ported the original model, which is just used to detect all objects really, to a Motorola E7 phone. So I just wanted to test its capability in actually detecting the location of a traffic light. So I test against common clear sky backgrounds. As you can see over here, these are against the sky. And then you can see it detects other stuff like car because this is not retrained yet. So these are the traffic lights it can register. And this is against like sky background and sort of buildings. And then this one's just against building backgrounds. So you can see there's a clear difference in the mean, but they're both pretty high, 85%, 70%. So the detection of traffic lights is it's rather capable of doing that, and there's confidence that it can be able to do this later on. So I would build upon this and retrain to detect the traffic light signal itself. And the YOLO V3 evaluation. So the YOLO 3 model is original implementation is darknet, so it's difficult to be ported to mobile devices. And so instead, I would leverage the high-level API Keras, which is created in Python. So I would convert the YOLO model into Keras, then run the Keras model in UPython, which is in order to test against the public dataset Kaggle from Kaggle, which is the Lisa dataset. And after running the Lisa against the Lisa dataset, these are the results. So you can see over here, this is the detection probability distribution. So this is like a bell curve, and the majority is clustered around 79 to 99%. That's a very high detection rate. And this is the basically the comparison like of the values. So this is how many actual lights there were, and these are the guesses the computer made. So this is the model made. So this is the predicted. And so this is the analysis of the data. So as you can see, 99.99%, very effective model. And the precision was very rather lower, but the recall is really high, which shows that the model made a lot of guesses, very responsive, which is desired. So in order to increase the precision, the recall will have to be lowered, but it's a trade-off that's supposed to happen. So transfer learning. So the next step would be transfer learning. So the original YOLO model has 61 million parameters, so that's very hard to retrain the whole thing. So, but by transfer learning, you freeze a lot of the already fine layers and then just retrain a couple. So by retraining the last 3 prediction layers, it would only take 37,000 parameters to fix. However, test results were really poor. As you can see, these are not good results. So this indicated that there need to be additional layers built upon the model. So we would reuse the YOLO 3 model for the traffic light and then develop extensions based on existing models by adding another layer. So the current output of the YOLO 3 is the bounding box, objectness score, and the class probabilities. The bounding box is useful because it shows the location of the image, but the which these coordinates right here, that's where the bounding box is. But the objectness and class probabilities are thrown out because the objectness is the traffic light, and rather what is needed is the traffic light signal. So those need to be changed, and we needed to extract the traffic light color itself, which is lost before the final prediction stage. So we either take the features before upsampling, and that basically means combining early layers and the final layers in the YOLO 3. And that's what this step does right here. These 33 appended layers at the end are supposed to extract the features that are lost during the computation itself. So this was the results of that, and as you can see, the precision is rather high for in-sample, of course, because that is the sample is trained again, so 80% almost. And the precision for the out-of-sample is 60%, so it's rather fair. And the recall for both is rather low, which needs to be improved. And that might be due to the different images used. As you can see here the success rate is really high, and here the success rate is really low. So this cluster occurs because the cluster of images for each group are different. As you can see here, the light shines on this stoplight rather extremely, and you can't really see, it blurs out the image. So this really confuses the model. And all the images in this cluster are taken in the same frame because it's a film that, basically the data set is taken through a film and cut into separate frames to make different images. And during that time of day when the film was taken, the sun was at that spot. So it really depended on the time period it was taken in. And then, so next step is to port onto the mobile phone. So the SSD model still need to be retrained. So there was 2 new classes introduced, which was the Go and Stop classes, and the rest were deleted. So the Go and Stop class were attributed to green and red, respectively. And after it was run through 6,000 steps, which took around 24 hours. And then it was then converted to a TensorFlow Lite file, then added into the asset folder of an Android Studio program. And then it was then downloaded to the Motorola E7 phone and then tested in various crossings. So these are the results from testing. So you see right here, these are all the Go lights, and the bounding boxes are highlighted around the traffic lights as shown, and you can see it's very accurate. The bounding box is not really slipping off. There's a couple of them that, as you can see, this one is a little off center. That's fine. That's mostly due to the times the program would take its image. So upon testing, the conclusion, the test results really support the argument that a CNN-based app is very promising, and it can offer people a low-cost solution to the problem. And transfer learning was able to identify the go-stop signal, but you need to add more layers and train a lot more. So in order for the model to be more efficient, there need to be more training with higher epochs and also added on layers at the end that pulled out certain features needed. So for the studies, the model can be trained on the cloud, and then that way with leveraging GPU offered by Google Cloud, there could be more computing power. However, Google Cloud does not offer GPU in free trial, so there might need to be some fundraising there. And then the GPS pairing, so that would allow for the app to be notified when close to a traffic light stop, and that way that could further the ability for it to be a real life solution. And there can also be more testing downtown in densely populated areas, which will create more noise for the model to adapt against, and this will improve the model even more. So that's my bibliography, and thank you so much for listening to my presentation. Hope you have a nice day.